full screen for just your slide here on
Oh,
the
okay.
Zoom.
Okay, I'll leave it be as is then. Okay, so today I'll be speaking about vector processors on FPGAs. So I'm working with the open source Pico Ice board. It has Ice 40 up 5K and a Raspberry Pi 2040. It's about $38. And what it does is, if you look at it, if you look in the vertical black bars in the middle, those are 30 block RAMs, which you'll be using for storing vectors. And if you look on the vertical bars on the edges, you have eight digital signal DSP blocks. So we'll use one for the soft core, fourth soft core, and we'll use the other seven for the vector processor. Um, the division of labor kind of reminds me of the movie from Butch Cassidy and the Sundance Kid where they run into the banditos. And Butch Cassidy says, you take the one on the right and I'll take the five on the left. Kind of the same division of labor. I don't know if you've seen those movies. What happened here? Okay, so the you end up with this hybrid computational model, which is partially sort of stack-based and partially register-based. So we have these vectors with about seven elements in them, and you can access them for some commands. You can access them as vector 0, 1, 2, 3, or 4. But for some commands, you don't have enough bits on a 16-bit machine, and so you really just have to assume that the results are going to be in the top of stack. And then if you need to swap those, you're going to have not swap, but swap for swap vector or swap2 or vector rote or vector rote minus. So there are four vectors, three of which are like real vectors, and one of which is a scalar vector. You can see in the lower left-hand side, you can set the scalar, and then that just fills all the elements with the scalar vector values for doing multiplies or adds. If you multiply two of these vectors, you get a vector that's twice as long. So that's called a product vector. And if you're doing I/O or something, you may have SPI that feeds in slowly, or you may have memory that only loads one item at a time. So you can have a shift vector that's either shifting in bits or shifting in entire words. And then when it's full, then you can start doing faster vector operations on it. So the basic idea of adding two vectors, you do a sum, all the elements get added together. And they're called lanes, right? So in every vertical column, you have a lane. I shift them a little bit just so the graphics is a little bit easier. So trafficking two vectors is another important one. We're using two complements here, signed items. Multiplying two vectors, this ends up giving a much larger vector, twice as large. So it's really kind of this hidden product vector, right? And the only thing you're going to do on a hidden product vector is shift the results and then take the higher order bits. There's a scale factor when you multiply, so you have to shift that scale factor out because it gets doubles when you multiply, and then you have to do a rounding. So a little bit of logic to do that. Scalar vector multiply. So we have a number five, and it gets replicated, and then it can multiply by another vector, and it goes to the larger vectors. So we end up with three vector instructions. So these are instructions that include three vectors, right? So we have the opcode. We're doing 5 bits of opcode. It's a 16-bit instruction. There's seven items in the vector. We may not want to use them all. So typically what people do is they have a mask bits. That's seven, that's plus five is 12. That only leaves four, which is for two for which of the two vectors is argument one, two for which of the two vectors is argument two. For most operations, it doesn't matter, but for minus, it does matter which one. Minus is not commutative. All the others are commutative, right? So, okay. Um, so we don't have enough space for a destination register, which is why the destination register becomes the top of the stack. If you have a if you have a larger instruction set, then perhaps you do have space for a third, and you can, but then you'll have more mask bits. So anyhow. The interesting thing comes when you get to vector storage. This is really the critical piece of it, right? I mean, there's some vector and single instruction, multiple data on CPUs, but they're limited in storage. Whereas on FPGAs, you have all these block RAMs. And so if you have a vector three vectors, then each of them gets a different chunk of a block of block RAMs, and then each block RAM is vertical, and so you can store an entire vector, and so you have a different number of different addresses that you can read or write the vector from, and you can read or write those vectors in a single clock cycle. So, so that's kind of the big benefit. And if you get a larger, the small FPGA for $8, you don't have that such large vectors, but you get a larger, um, like the another one of the FPGAs has for $50, you can get like 64 grams. So you can get massive vectors for very, very small amounts of money. So then again, you have vector load store operations. There's an opcode. Uh, there's a 3-bit mask. So which of the vectors are you storing, and an address that you want to store it to. So you can actually store all vectors, since they each have their own block of memory, you can actually store all three vectors at the same time to the same address. You can do shifters. So here you're getting into two arguments, right? Because you have which vector you're shifting on and which vector is the result. In this case, both the input and the output are on the same vector. You have a scalar that tells you how much you shifted by. And so if you look at the instructions for left shift, right shift, you have a shift amount. So that's going to be 5 bits, depending on how large your storage size is, which vector it's from, which vector it's to. There's a separate, if you're shifting the double-sized vector, then there's going to be a separate command. So you still only have 4 vectors that you address. Sums are another one. Sums generate the scalar, so you only need one vector. It's a single argument, but you may want to sum like 14 long vectors. So then you may want to use the total from the previous. You have one bit that specifies that also. You may want to read the output of your vector, so you need to be able to specify which vector you want to read and which element in that vector. So what you do is you get read instruction has an opcode, it's got an index. For 7 vectors, so the two vectors the from on the right hand side tells you which of the 3 vectors you want to read from. The index just to the left of it tells you which of those 7 values you want to read from. You can have a scalar right. Again, you can use the mask. So maybe you want to zero out all the elements, but you don't want to zero out some of the elements. And so that's going to give you mask and then the opcode, and on the right side to which vector you want to be writing to. Then you have a couple vector operations. Well, I guess they don't use the vector at all. You have a scalar, right? So you may want to fill the scalar with some value. So you can either fill it, you have 5 bits for the opcode, a 16-bit instruction. The value can then be, you've got 11 bits. So you can write to the low bits, 11 bits. You can write to the high bits. If you need to fill all of them, you can use 2 instructions to overwrite all 16 bits. Also, eventually this will have its own instruction space so that this can run independently of the 4th core or the whatever soft core you're using. And then, so then you need to be able to write the scalar to either write or read it from memory, so that you can write a program to memory, or you can read a program from memory to make sure that you've got it right. So 0 vector operations. Maybe I should call them scalar operations. So matrix multiplication. So typically in matrix multiplication, you do 1 row by 1 column. So this works really well because on every clock cycle, you can sort of in a pipeline fashion read the two vectors and multiply them and write them out again. Of course, GPUs do matrix multiplication very well, but just give you an idea of what, and probably certainly much better, but just give you an idea of what's possible. So a lot of the CPUs have some of this stuff, but where you really get the advantage is as soon as you start doing application-specific stuff. So for example, here we're interested in music generation, and a big feature of like there's AMI software on microcontrollers. A big feature is sine wave generation. So the way you generate a sine point, one way to generate a sine point is using table lookups. So if you look at the top of the page, there's sine of A plus B is sine of A times cosine of B plus cosine of A times sine of B. So basically, if you look on the left-hand side, you can see what the A bits are and the B bits are, and you basically split it, the high-level bits on A, followed by the low zeros, and the low-level bits on or the B with the high-level zeros. And so then you just have an um, two table lookups, each with 8 bits. So 8 bits gives you 256. So actually, in the ICE40, that's 2 grams. You actually need four because there are 4 times you're doing looking up, and you can do all of those four lookups at the same time, and you can populate the vectors with those values, and then do the sum and the right product shift and rounding. So this is kind of so whereas vector multiplication may be a little bit faster than the RP2040, once you start doing application specific stuff like this using the vectors, then suddenly things get much faster. And particularly, that's a bit better. And if you start doing a pipeline, so this one's a little bit hard to follow, right? So you're going around in a circle, you have some angle, and you have a delta to it. The delta's in the upper right-hand corner. I don't know if you can see if I click on this stuff. So you take a delta and you add it to the previous A plus V values, and you get a new A plus B values. And then you feed those on the next clock cycle, you feed those into sine A, cosine B, cosine B. And then you multiply those. So those go down on the large product vector, and then you do the bit shifting and rounding. You bring it back, and finally you sum them, and it goes through saturation. And then at the bottom, you can generate your output vector. So so usually on CPUs, if you do a pipeline and you have a jump, you toss it all out. But on math operations, we're not going to have a jump because we know what we're doing. And so you can actually just save these vectors, and then you can reload them all again, and just continue right back from where you were. So again, that speeds things up. The bandwidth to memory is really the key winner when you're doing FPGA vector operations. Another one in real-time control is often you have to estimate stuff, and so people do finite input response filters and infinite input response filters. So a finite input response filters just take some product of the previous values, multiplies them by some scalar and adds them together to get the new value. Infinite um, input response filters, they actually have two vectors that they multiply. There's some scale factor. They multiply it by the samples, but they also multiply it by the previous estimates. And so what you can do with the masks is you can actually do both of those sets of multiplications at the same time. So that speeds things up. I'm not a big fan of artificial intelligence, but it's very much vector centric. So if you can do large numbers of so you should basically do 1 neuron per second on this type of vector processor. The more interesting one is the FFT, and this is kind of new to me just by a few hours, but you have these kind of butterfly networks where you have to take the values and you shift them. So you take your vector of data and you alternate the bits. You alternate the values, and the even ones go to one side and the odd ones go to the other side, and then you do that recursively. So you can do that kind of thing very nicely on a vector processor. Here we have a FFT on a larger FPGA. This is the $50 one from Cologne Chip. And Olimex. And so basically what you can see is you can see the raw data and it gets split into the odd and even parts. And so every alternate one goes to odd and every alternate one goes to even. And then you input the next vector of 32, maybe it's loading in the background. You input the next vector of 32 elements, and then those also get split into the odd and even pairs. And then once that's all done, then you do the same kind of splitting on odds and evens and so forth. So anyhow, this is one way to do it. There are a couple other ways to do it. I'm still not sure about the optimization, but it's an interesting example because this is the kind of thing that completely will outperform a regular CPU. I mean, you just don't want to be doing this on regular CPUs. Okay, so then everybody asks, what about the RISC-V vectors? So there is a spec for RISC-V vectors, and RISC-V has 32 registers, and typically on small ICE40 devices that requires massive multiplexers, and so people don't do them. They just store them in memory, and then they have to read and write them. So, which is why stack machines are faster on small FPGAs. But I mean, you really don't want to be storing 32 vectors, and then how do you load them all and stuff, right? So the whole RISC-V model doesn't make sense, and there's some issues when you move it to ASIC also because they have their mask in the first element, and so then that doesn't scale across the rest of the vector well. But okay, anyway, that's comparative market analysis. ARM SIMD is interesting. The Raspberry Pi 2350 actually has two cores, each with 32-bit registers, and they can each do either 8-bit or 16-bit operations at a time. So, okay, that gives some kind of vector stuff, but do you really want to mess with vectors running on two different cores? I mean, if you're doing a vector, you want it on one core. It's way too complex if you have to juggle stuff between two cores, right? So, and then FPGA, you can do variable bit width, you can do variable vector length, variable instruction set. So, certainly for the mass market, the ASICs are better, but as soon as you want to customizations, you want to be doing vectors on FPGAs. ARM Neon is the newer one. This has a 128-bit interface to an L1 cache and L2 cache. That's like 8 by 16-bit vectors. Well, that's starting to get much more interesting for load speed. Of course, L2 is slower than L1. Is it 2 clock cycles, 3 clock cycles? I don't know. The whole ARM Neon thing, there's not such good documentation. I can't quite, it took a while to figure it out. Evidently, there's like some IRC group where the guys who do this hang out, but not very clear. Um, for basic RP2040 versus ICE40 UP-K, question is how long does it take? Well, on the RP2040, to fetch the first argument takes 2 clock cycles. To fetch the second argument takes 2 clock cycles. Multiply takes 1 clock cycle. Rounding takes 3 clock cycles maybe. Shift takes 1 clock cycle. Incrementing the count, doing a store, conditional branch. That's 13 operations to do one multiply. If you're doing comparing to 7 multiplies, that's 91 operations, and 6 adds comes to, oh, sorry, 97, a little bit less than 100 at 135 megahertz, so about 1.35 mega dot products per second. On the ICE40 up 4 or 5K, you 2 to 3 clock cycles for a dot product, one dot product cycle at 50 megahertz divided by 3. It comes about 16 mega dot products per second. And that's a really small FPGA. If we go for this Cologne chip one, you can easily do 32 wides, and so we get much better performance. Um, and then what do you do with this thing? Well, for music, maybe this kind of Bandit fourth computer, $170 is kind of a nice form factor. I was just spoken about last month here at Silicon Valley Fourth Interest Group. The new one has a little display, which is great for musicians. Maybe they want to display FFTs. Well, the nice thing is you can take one of these ICE40 chips and pop it in their SSD drive and then have it do the FFT calculations for you. And so the way that works is you use the Signaloid micro SD card. Um, so $40 will get you one of those, and it just pops right into the SSD drive. Maybe you want to do wireless stuff. So there's a $99 ICE-V wireless board with an FPGA and a ESP32 on it. It just runs at 60 megahertz, a battery charger, Bluetooth, Wi-Fi. The one that's interesting me increasingly is the Olimex GateMate, right? So that also has, just like this one, it has the Raspberry Pi 2040, but the big difference is there are a lot more wires between the two chips. And so it's got like 28 wires instead of 10 wires on the PicoIce. So you can get much higher bandwidth, right? So you can transfer a 16-bit, heck, you could transfer the 20-bit wide instruction one per clock cycle. And what they run at 150 megahertz. A number of grams, the PicoIce FPGA has 30 grams, so 7 vectors or something. The Olimex GateMate has 64 grams, so you can do much larger vectors. On the PicoIce, each gram has 256 16-bit items in it. On the Olimex GateMate is 1024. RAM with the 16 bits, 20 bits on the GateMate. 16 bits is fine for music, but for real-time control, I think you really want to be at the 20-bit stuff. So that interests me. Number of logic elements, PicoIce has 5,000. Olimex GateMate has 20,000. DSPs, you're limited to 8 on the PicoIce. 16 by 16. The GateMate does 20,000 2 by 2s, which comes out to about 160 16 by 16, if I did my math correctly. And then PicoIce doesn't have a case. Oh, I got those columns backwards. Whereas the Alimax GateMate does have a 12 euro case. So one is $38 plus sort of VAT import duties in Europe. Alimax GateMate is just $50. No, here in Europe, no VAT or import duties. So I missed one more slide. Let's see. Okay, just check something. Yeah, okay, I did the FFT. Okay, any questions?
Now, I've got a question as a fairly naive um, person on all of this. Is each numeric element of the vector 16 bits?
So that depends on the particular FPGA. The ICE40 is limited, the grams are limited to 16-bit wide. On the Alimax GateMate board, the grams are 20 bits wide. So there are other ones that are 18 bits wide. So you can and you can add them up like 18 plus 9 or something. So you can make your items basically different sizes, whatever you need based on which boards you use.
Okay. If I'm synthesizing sound, is each vector a sample? And so to make a sine wave, you then would have a sequential samples, or does the vector itself define the continuity of a sine wave in its entirety?
Right. So typically CD audio is 16 bits. So at whatever 44 kilohertz, you get one 16-bit for every 44,000 times a second signal when you have an audio signal on CD quality audio.
Okay, well, a vector is an assembly of integers then, isn't it? So is one vector just one point and it's 16 bits, or does that imply there's a series of values that compose the vector?
Yeah, so one point is 16 bits, which gives you 64K, which is the resolution of audio. So every time step, you have one point. And so a vector is like this infinite stream, and a vector processor can process 7 or 32 elements at a time.
So there's a pipeline then that comes into the processor of these sequential values, and it's
Yeah, so let me
processing them in
actually,
order.
exactly, let me go back here too. So the vector processor processes, say, 7 or 32 or however many items at a time, right? So there'll be 7 signals, right? But you may also be reading data in from SPI or I2S or something, and that would go into like the shift vector. And then when the shift vector is loaded with the 7 items, it can get copied into the vector processor. So data comes in one element at a time every so many clock cycles, every measurement period. Um, and so the frequency of collecting data is going to be different than the frequency of processing data, right? So you collect data one every so many clock cycles, but then you process a vector, all the items from, say, 7 time steps in one vector at one point in time.
So it's putting the incoming information into chunks, and it's processing each chunk as a group of elements.
That's correct. That's right. Right. So you have a bunch of samples, like data samples, and you group them together into a vector. That's correct.
Okay. Okay. Very good. Thank you.
Good question.
How how do you get the information into this now? Do you have like A to D sampling that's done somewhere externally?
Yeah, so this is my layout of where I'm going. I mean, how do you get um I mean, you can use it to either do this for music synthesis. There's some program maybe on the Raspberry Pi that tells on the Raspberry 2040 that tells you, or for data processing, you're getting your data in from outside. If you're getting your data from outside, you're going to be doing some filtering on it. You're going to be doing some low pass filtering or some high pass filtering or um, finite sort of infinite input response or finite impulse response filtering. And so then you would, bring your data in, you'd filter it, and then after you filter it, then you'd do whatever it is you wanted to do with it, right? So kind of you'd read your data in, process it through this, and then process through it again to generate whatever your output is.
Okay, I guess the last one is, I'm inferring that you're working toward writing a fourth sublanguage that's the assembly language for this chip.
Yeah, so basically what happened with the fourth soft cores is no one's really that interested in them, and I can understand that why. Whereas the vector processing gives you just significant performance advantages over regular microprocessors, right? And so this is really think of it as a floating point coprocessor. So you end up with a programming language for it, and the programming language is a cross between, for the small devices, it's a cross between sort of actually, if you can see here, we've got the fourth-like instructions. Say for two argument operations, you can specify the two vectors. But if you have three argument operations, you have to put the result in the top of stack. And so because the top of stack may be full, you may want to rotate it out. So you do get the fourth operations, swap, swap2, vrot, and vrot minus to rotate those out. So it's kind of so it will have its own instruction set, and you can drive it from a fourth or you can drive it from something else. The reason for driving it from fourth is because the fourth soft cores are smaller, their memory requirements are smaller, they're faster, they can execute one instruction every second, every clock cycle. The small RISC-Vs, the registers, there's so many registers, they don't have multiplexers on these ICE devices, and so they end up not being able to access the registers immediately. They store all the registers in memory, and then they have to go out and read them and write them again. And so it's very much slower. So there's a whole bunch of reasons to use a fourth soft core with something like this, particularly for debugging and synthesis. In simulation, you can run the fourth soft core inside the simulator. So there's no interprocess communication with like a Python debugger. So it's really good for developing in simulation, and the fourth soft core is really good for controlling something like this on an FPGA. But the reality is that they're just not interested in fourth soft cores. But vector processors, even in this conversation, I'm getting a lot more questions than I did previously.
How are these classically being programmed currently?
So the big one is ARM. There are 2 or 3 instruction sets. Let's see if I can find it. So first of all, generally people don't use them. They just do regular programming, right? There's the single instruction, multiple data, and there's some APIs for using it. And then there's a new API that uses the ARM Neon stuff. But it's sort of, when first I went and looked, I couldn't figure it out. And it was kind of, maybe there's a third API also. It's just confusing, and there's a sense that people don't do it much. Don't forget that vectors are sort of an engineering concept, right? So if you're an engineer, you want to do this. But a lot of programmers sort of, I don't know if this is true or not, but maybe a lot of programmers haven't had a lot of engineering training and don't do a lot of this math stuff, right? So it's, so anyhow, the competition isn't clear to me. Part of me was hoping somebody here would have experience with it and could educate me more. We'll see.
I can say that certainly this is still, coding for these instruction sets like Neon and the Intel equivalents are definitely something people still do by hand, because it's, you sort of need to hand tune it and things like that. So and you need to take the cache effects into account, that type of thing.
So, and do people do a lot of this stuff? Have you seen a lot of this stuff?
The main domain I've seen it in is for implementation of codecs. So if you're implementing like a video codec, things like that, you want to squeeze every last drop out, and so folks will do this for decoding video or image or audio codecs, and they'll kind of very carefully lay things out in memory, and that's and then worry about hand tweaking them to get maximum performance to run stuff like a bleeding edge codec on our hardware or other.
And then they have to worry about the L1 and L2 caches and optimize all of that also?
Oh yeah, and I mean it's like another example I know of is the implementation of some of the computer vision stuff for tracking of and overlaying of hats and things in some of the video conferencing software. That tends to be something where folks will spend time hand tuning it because they want it to run on a wide range of computers, and so they'll often do one implementation for even different generations of like Intel hardware, that type of thing.
Yeah, and so clearly the vector processing is huge for image processing also. I didn't talk about that yet. I'm just starting to scratch that area.
Yep.
Dig into that area.
Have you touched on CUDA and like OpenMP?
Right. So CUDA is one of these GPUs, right? So so those things have so first of all, I don't think they're cheap, right? I mean, when I poked around, typically a graphics processor is sort of hundreds of dollars, and they're amazing for vector multiplication, right? So matrix multiplication, don't even think of competing. But as soon as you're they have a particular computational model, but the computational model isn't really a vectors, right? So one of the things with both forth and vector processing is you really want a very simple computational model. You don't want to be messing with L1 versus L2 caches or how to map this over to right. So maybe a biggest argument is this a clean concept that makes it easy to program, fast and easy to program, right? But so I don't know as much about graphics processors as I showed, or the competition in that area. But certainly, I mean, if you're doing straight matrix multiplication, no chance. But probably if you're doing FFTs, then maybe they don't do very well. The whole market competition, where exactly to go with this is one of the things I was looking for this group is kind of sort of educated feedback is which direction I should take this. Is this a good idea? Is it not a good idea? So the music is one direction. This is actually one of the people here recommended this one article about how to do music synthesis using this kind of vector math. So for the hobbyist market, clearly that's one very useful place. And so the question is, are there any commercial markets for this stuff?
On the hardware side, I'm not sure I could say. My sense is, at least for software side, a lot of the constraint is that folks are, will try to do stuff that's available in the instruction sets of the devices that are out there. So there's this kind of, what's in the market. And
installed base.
Sorry, what was that?
It's the installed base issue.
Exactly. And definitely in general, even with the GPUs, a lot of what sort of the secret sauce is about kind of optimizing how it's handling, making sure that the thing is fed and that the caches are full and so on. So
so I think the whole memory management is a big part of it.
Yeah, absolutely.
Are we ready to move on? Any last quick questions? Okay, Chris, thank you so much.
Thank you.
Did you de-share? So this is the part of the meeting where we take a screenshot of the mugs of you guys. If you're on the LAM, turn off your camera or log out or change your name to I'm not here or something. I understand if you put a dot in front of your name, you become invisible. No, that's Unix. Sorry. We digress. So, everybody ready for the screenshot, Brad? Brad can't give us a count, so look your best now, and
all right,
he'll tell us when you don't have to anymore.
Like an old-timey camera, hold still for a few seconds so we get it in the moment. 1, 2, 3. Okay, I got it.
Unfortunately, Christopher's brain is so big that he doesn't fit in frame. All right, on with the show. Bill will introduce himself, and Bill, you're on. We can see your screen.